The year is 1945. World War II ends with atomic blasts over Japan. But across America, 170,000 steel-curved buildings face an uncertain future. Nobody planned for victory this complete. Nobody planned for peace this sudden. These are Quansit huts, military surplus now. Each one cost $1,294 to build. Each one housed 36 soldiers through typhoons and bombing runs. Now they sit empty on bases from California to Maine. What happens next changes American housing forever. Veterans flood home to find no homes waiting. The construction industry spent 4 years building bombers instead of bedrooms. Families double up in apartments. Some live in converted chicken coops. Others pitch tents in city parks. Into this crisis walks surplus Quansit huts, available for $1,000 each, complete buildings, weatherproof, move-in ready. The federal government practically gives them away to veterans. By 1946, entire neighborhoods spring up, made entirely of curved steel homes. Roger Young Village in Los Angeles houses 750 families. Fairview Addition in Portland becomes home to 350 families. These aren't temporary solutions anymore. They're communities. Families paint their steel walls cheerful colors. They add wooden porches to hide the military origins. Gardens bloom around curved walls. Children play between structures that once sheltered bomber crews. Churches discover Quansit huts solve impossible math, too. Growing congregations need worship space immediately. Traditional church construction takes years and costs fortunes. A surplus hut costs $1,500 and opens for services next month. First Presbyterian of Levittown, Pennsylvania, holds worship in their steel sanctuary for 15 years. The acoustics are terrible. The aesthetics underwhelm. But people gather for prayer every Sunday under that curved ceiling. Schools face the baby boom explosion. Enrollment doubles overnight. Conventional classrooms take forever to build. Rural districts especially embrace Quansit classrooms. One hut houses 30 students for 1/10 the cost of traditional construction. By 1950, over 3,000 American schools include at least one Quansit classroom. Entire generations learn reading and arithmetic under curved steel roofs. These temporary solutions last decades. Small businesses join the revolution. Machine shops, auto garages, warehouses. The clear-span interior needs no support columns. Perfect for industrial work. A welder sets up shop for less than 2 months' rent elsewhere. Farmers rediscover what the original Strand Steel Corporation knew. These buildings make perfect equipment storage. Grain bins, livestock shelter. Maintenance requirements are minimal. Hose off the exterior annually. Check bolts occasionally. The structure lasts forever. This civilian adoption creates accidental architectural legacy. Quansit huts embed themselves in American visual culture. They represent practicality over pretense, function over form, making do ingenuity. Movies and television shows use them as shorthand. Post-war optimism mixed with austerity. Architectural historians initially dismissed them as eyesores, but by the 1990s, preservationists recognize their importance. Several achieve historic landmark status. Now let's rewind to December 7th, 1941. Pearl Harbor burns. Within 72 hours, the military faces logistics nightmares having nothing to do with battleships. Across the Pacific Theater, American forces sleep in canvas tents. These disintegrate under tropical downpours within 3 weeks. Field reports describe supply depots flooded, ammunition ruined, soldiers hospitalized with pneumonia because their shelter literally fell apart. Traditional wooden barracks require skilled carpenters. Weeks of construction time. Lumber that doesn't exist on remote coral atolls. The Navy calculates 18 months to build conventional housing for forces they need deployed immediately. In Washington, Brigadier General Eugene Raybould stands before crisis tables covered in weather maps. His engineers present impossible equations. They need structures manufactured in Pennsylvania, shipped 10,000 miles through submarine-infested waters, assembled by exhausted Marines who never held wrenches, surviving everything the Pacific throws at them. 130-degree heat, Category 5 typhoons, monsoons dumping 15 inches in 6 hours, Japanese bombing runs. Standard Army tents cost $12. They last 1 month in jungle conditions. Wooden barracks cost $8,000. They require construction crews for 6 weeks. Neither works when island hopping across the Pacific, needing shelter for 50,000 men yesterday. The British fought longer. Their North Africa experience offers clues. Since 1916, they've used Nissen huts, semicircular steel shelters invented by Canadian engineer Peter Nissen during World War I. These corrugated iron half-cylinders house 30 soldiers. They require no skilled labor to erect. They laugh at sandstorms, but Nissen designs have critical Pacific flaws. British versions use heavy steel panels needing specialized lifting equipment. The ventilation works for Libyan desert, but creates steam cookers in Philippine humidity. Each hut requires custom foundation work, concrete pouring or wooden platforms, right back to the carpenter problem. Raybould's team calculates shelter needs for 2 million personnel across hundreds of islands. The math is brutal. At conventional construction rates, the war ends before half the troops have roofs. Soldiers write letters home describing boots full of rainwater, fungus growing on uniforms overnight, temporary tents collapsing during storms, men scrambling in mud at 3 a.m. Medical Corps reports respiratory infections hospitalizing more men than enemy action in some sectors. This isn't about comfort. It's about maintaining fighting forces that don't rot away before seeing combat. The call goes out to American engineering firms, university research departments, Navy construction battalions. The specifications sound like science fiction. Design buildings weighing less than jeeps, fitting on single rail cars, requiring no foundations, assembling in 1 day with basic tools, costing less than $1,000, surviving conditions, destroying permanent buildings. Oh, and have 10,000 units ready in 6 months. It's February 1942. Somewhere in Rhode Island, engineers are about to turn architectural impossibility into reality. The Nissen Hut blueprint arrives at the Navy's Bureau of Yards and Docks through wartime cooperation. British engineers, grateful for American supply shipments, share detailed technical drawings. 16-foot-wide semicircular tunnels made from corrugated iron sheets bolted to wooden frames. Commander John Philip Driscoll studies specifications. He sees genius and problems immediately. The genius: arch shapes naturally deflect wind and shed water without complex engineering. The problems: a laundry list dooming the design in Pacific conditions. British huts weigh 3 tons disassembled. They require foundation bolts drilled into concrete. They use internal wooden frames, becoming termite feasts in tropical climates. Driscoll circles ventilation specs in red ink. 2 small windows designed for Scottish weather would create ovens at Guadalcanal's 98-degree average temperature. Another American voice enters this conversation from unexpected corners. Buckminster Fuller preaches prefabricated housing since the 1920s. Most architects dismiss him as a crank. His Demaxian house concept reads like prophecy in 1942. Factory-built, lightweight, assembled on site. Fuller's ideas about mass-producing housing like automobiles Sound less crazy when your country needs entire cities' worth of shelter every month. The military doesn't directly consult Fuller, but his published papers circulate through engineering departments. His core insight proves invaluable. Treat buildings like manufactured products, not construction projects. The Navy consolidates thinking at Quansit Point, Rhode Island, a freshly commissioned air station on Narragansett Bay. The location isn't random. Rhode Island has deep sheet metal manufacturing expertise from jewelry and silverware industries. Plus, proximity to Pennsylvania steel mills and shipyards, understanding marine-grade corrosion resistance. March 1942. The Navy assembles unusual teams. Structural engineers from Strand Steel Corporation building prefab farm buildings. Architects from George A. Fuller Construction, specializing in rapid assembly methods. Navy officers who actually served in the Pacific, knowing what typhoon-proof really means versus paper specifications. Team leader Otto Brandenberger brings farm building experience exactly right for this problem. His Strand steel barns use self-supporting arched panels. No internal frames needed, no wood for termites, no complex joinery failing during storms. Brandenberger's radical proposal: eliminate Nissen huts' wooden skeletons entirely. Make corrugated steel skin carry all loads. This violates conventional architectural wisdom, where steel is for bridges and skyscrapers, not self-supporting buildings. But Brandenberger knows his barns survived Midwest tornadoes without internal framing. He's willing to bet the same principle scales up. British contribute crucial elements through painful experience. Their Nissen huts in Burma and Singapore taught exactly how tropical environments destroy buildings. Fungus isn't cosmetic. It literally eats through wood preservatives and paint within months. Humidity doesn't just dampen things. It corrodes metal fasteners until roofs collapse. Insects aren't merely annoying. Carpenter ants reduce wooden beams to hollow shells in one season. British reports read like horror stories, but they provide Quansit teams with checklists of everything engineered out from day one. No wood contacting ground. All steel hot-dipped galvanized, not painted. Ventilation aggressive enough preventing condensation. Every fastener accessible for replacement without disassembling structures. By April 1942, hybrid visions crystallize. Take Nissen huts' brilliant arch geometry. Strip out everything heavy or vulnerable. Add Fuller's mass production philosophy and American steel manufacturing muscle. Engineer every detail for Pacific Island warfare's specific hell. April 15, 1942. Otto Brandenberger walks into Quansit Point warehouses with 30 engineers and laughable deadlines. 60 days to design, prototype, test, and approve completely new building systems that don't yet exist. Teams work shifts around the clock, sleeping on cots pushed against warehouse walls, subsisting on Navy mess hall coffee, and pressure producing either brilliance or complete collapse. Brandenberger divides crews into specialist teams. One tackles aerodynamics and structural loading. Another figures out nesting components for shipping. A third works exclusively on joint and fastener problems plaguing British designs. The first radical decision happens day 3. Traditional architectural drawings take weeks. Teams don't have weeks. Instead, they build in real time. Sketch details mornings. Have metal working shops fabricate by afternoon. Test overnight. Revise by dawn. This iterative prototyping is standard in 2025. Revolutionary in 1942 when buildings are designed completely on paper before cutting single pieces. Warehouse floors become laboratories scattered with failed joint experiments. Bent test panels. Increasingly refined component versions. engineers steal techniques from aircraft manufacturing. Every part gets numbers. Every revision gets documented. Nothing moves to next prototype generations without solving previous failures. Dimensions come from brutal practicality rather than aesthetic choices. 16 feet wide. Maximum fitting standard rail cars without special permits. 20 feet long per section. Short enough for 4 men lifting panels, but long enough creating usable interior space. 48 feet total assembled length. Housing capacity for 36 men with bunks, converting to offices, medical stations, or supply storage. Quansit teams discover this size hits structural engineering sweet spots. Smaller wastes shipping capacity. Larger makes panels too heavy for field assembly or requires internal supports, reintroducing eliminated problems. Arch radius calculations consume 2 full weeks of 60-day deadlines. Too flat and wind forces peel structures like sardine cans. Too steep wastes interior headroom and creates difficult end wall geometry. Brandenburger's team settles on 8-foot radius, perfect semicircles providing 7-foot headroom at sides, creating what structural engineers call self-bracing arches. Corrugated steel naturally wants holding these curves. Panels can be thinner and lighter than flat sheets, requiring same strength. Load calculations show designs theoretically handling snow loads up to 40 pounds per square foot. Wind speeds exceeding 100 miles per hour. But theoretical calculations and Pacific typhoons are different animals. By day 40, they have something looking like it might work. Frankenstein's monsters of riveted panels, experimental joints, borrowed hardware. First complete prototypes go up May 25, 1942. Assembled by 6 sailors given 4 hours instruction and basic hand tools. Assembly time, 14 hours. Encouraging, but not good enough. Navy wants single-day construction capability because marine landing schedules don't allow multi-day building projects. Teams identify bottlenecks immediately. Floor systems. They've been trying including wooden floors as package parts. But it's the slowest assembly part, and first thing rotting in tropical conditions anyway. Solutions are elegant in simplicity. Eliminate floors entirely from basic designs. Huts sit directly on whatever surfaces exist. Coral, sand, dirt. If you're lucky, gravel. For applications requiring finished floors, those add later as separate projects. Basic shelter achieves weather protection without them. This single decision cuts assembly time to 8 hours. Reduces shipping weight by 1/200 pounds per unit. June 10, 1942. Final prototypes stand complete. 96 corrugated steel panels, each weighing less than 50 pounds. Bolting together, creating 720 square feet of enclosed space. Total materials cost, $1,294. Total weight, 9,000 pounds. Real tests begin when Quansit prototypes face engineering interrogations. Navy structural engineers arrive with wind load tables. Typhoon data from Pacific meteorological stations. Healthy skepticism that corrugated tunnels survive what nature throws at tropical islands. Numbers they're working with aren't theoretical. They're pulled from actual weather events. Typhoon Gloria hit Guam November 1940 with sustained 140-mile-per-hour winds and 180 to-north gusts. The 1935 Labor Day hurricane killed 400 people in Florida Keys. It produced winds so powerful they sandblasted paint off buildings. Drove wooden planks through palm trees like spears. If Quansit huts fail in storms, results aren't property damage. They're dead servicemen and destroyed equipment. Brandenburger's team starts with fundamental physics of why arch shapes work. When wind hits flat walls, it creates what engineers call pressure coefficients. Wind pushes directly against surfaces with maximum force. Curved surfaces deflect wind upward and around, reducing pressure dramatically. Think how water flows around river stones versus slamming into dam walls. Semicircular Quansit profiles mean hurricane-force winds slide over structures rather than trying to punch through them. Corrugations add second layers of brilliance. Those ridges running lengthwise create structural rigidity. The way folding paper makes it stronger than leaving it flat. Each corrugation acts like tiny I-beams resisting bending forces that would crumple smooth sheet metal. The math gets fascinating examining how loads distribute through arches. In conventional rectangular buildings, roofs push down on walls. Walls push down on foundations. Everything depends on vertical load paths staying intact. Storm winds literally lift roofs off because they're separate elements sitting on top of walls. Quansit arches change this completely. They're single continuous curves where every panel shares loads with neighbors. Engineers call this compression rings. Same principles keeping stone bridges standing centuries without mortar. Hoop stress, tension trying to spread arches apart at bases, gets resolved by ground itself. Each Quansit panel bolts to adjacent panels with 3/4-inch steel bolts spaced every 6 inches, creating what's essentially 48-foot-long steel cables wrapped in arch shapes. But theoretical strength means nothing without testing. Navy sets up validation experiments bordering on sadistic. They build full-scale Quansits at Davisville, Rhode Island. Instrument them with strain gauges, pressure sensors, deflection meters, then wait for first major nor'easters. March 3, 1943. Storms hit with 75-mile-per-hour winds and heavy snow loading. Perfect test conditions. Instruments record structures flexing less than 2 inches at ground, then returning to original shapes when winds subside. Panel joints hold. Nothing leaks. Structures behave exactly as calculations predicted. This is thrilling and slightly terrifying. It means they're about to bet thousands of lives on these designs. Tropical environment testing proves more challenging than wind loads. You can't simulate years of jungle conditions in Rhode Island warehouses. Navy ships test units to Panama Canal zones where humidity averages 85% year-round. Temperatures stay above 80 degrees. 6 months later, reports come back. Minimal corrosion on galvanized panels. No structural degradation, but serious interior condensation problems. When hot, humid air hits relatively cooler steel at night, water literally rains from ceilings inside huts. Solutions require adding ventilation louvers at both ends and along ridgelines, openings letting hot air escape, and creating airflow without compromising structural strength or weather protection. These vents add $47 per unit cost, but transform huts from steel saunas into something humans actually occupy in tropical heat. Final engineering challenges are foundation questions. How do you anchor 9,000-pound buildings to loose sand or coral without pouring concrete? Answers come from tent technology scaled up. Steel stakes driven into ground connected to huts' bases with adjustable tension cables. For harder surfaces, teams design bolt patterns letting huts mount directly to wooden sleepers or pierced steel planking. Beauty of these systems is forgiveness. Structures can flex slightly with ground movement without tearing themselves apart. June 1942. War Production Board approves Quansit hut manufacturing. What happens next is American industrial capacity operating at absolute peak. Navy contracts with 10 major steel fabricators across Midwest and Northeast. Companies making grain silos and water tanks 6 months ago retool for military shelter production. Strand Steel Corporation converts entire Penrose facilities outside Philadelphia to exclusive Quansit production. George A. Fuller Construction takes over former automobile parts plants in Chicago. Great Lakes Steel dedicates 2 rolling mills to nothing but corrugated panel production. By August, these factories collectively produce 1/500 complete huts weekly. Numbers keep climbing. Manufacturing processes borrow heavily from automotive assembly line logic. Massive steel coils arrive by rail. Each coil is 4 feet wide, containing enough steel for 30 panels. Rolling machines corrugate flat steel, creating structural ridges at precisely 2.67 inches on center. Corrugating processes work-harden steel, making it stronger than flat sheets going in. Next, panels go through galvanizing tanks, where they're dipped in molten zinc at 850 degrees Fahrenheit. This zinc coating isn't paint. It's metallurgical bonding, sacrificing itself to corrosion before underlying steel rusts. In Pacific saltwater air, galvanizing means differences between 5-year lifespans and 50-year lifespans. Processes cost extra $112 per hut, but prove non-negotiable after field reports show ungalvanized steel corroding through in 8 months. Each complete hut kit gets packaged with obsessive shipping logistics attention. The 96 corrugated panels nest inside each other like stacked bowls, reducing package heights from 8 feet to just 14 inches. End walls, plywood sheets with pre-cut door and window openings, pack flat between steel panels. All fasteners, bolts, and hardware get boxed in single wooden crates, including illustrated assembly instructions designed for men who might not read English fluently. Entire kits load onto standard flatbed rail cars measuring 40 feet long. This packaging density is crucial because every train heading to West Coast ports carries either Quansit huts, ammunition, food, or vehicles. Zero room for inefficient cargo. Shipping choreography gets wild. Trains leave Philadelphia and Chicago daily, arriving at San Francisco, San Diego, Seattle, where Liberty ships and specialized cargo vessels wait at docks. Longshoremen load complete huts into ship holds using crane systems designed for tanks and artillery. Single Liberty ships carry 200 Quansit huts plus assembly hardware, representing shelter for 7,200 men. War Shipping Administration tracks every cargo manifest because these aren't just buildings. They're strategic assets. Huts shipping to Guadalcanal in September might house bomber crews by October, making differences between operational aircraft and pilots sleeping in mud. Assembly processes on receiving ends are where Quansit design genius really shines. Navy's construction battalions, famous CBs, develop standardized procedures turning shelter erection into choreographed operations. 6-man crews, 8 hours. 1 complete hut ready for occupation. Processes start with site preparation. Level ground. Remove vegetation. Lay down gravel bases if available. 2 men handle end walls while 4 wrestle steel panels. Panels overlap by 6 inches and bolt together with 3/4-inch fasteners. No welding required, no concrete needed, no skilled trades necessary, just wrenches, levels, and men following illustrated instructions. Speed records get set on Espiritu Santo, January 1943, when specially trained CB crews erect complete huts in 4 hours 17 minutes. But that's showboating. Real achievements are sustained production across hundreds of islands where crews throw up 5 or 6 huts per day. Day after day. Building entire bases faster than Japanese can bomb them back to rubble. By December 1943, monthly production hits 8,000 units. Logistics networks move so efficiently that huts ordered in Pennsylvania reach New Guinea within 40 days. including ocean crossing and trans-Pacific transport. Cost accounting tells victory stories. Each Quansit hut provides 36 men with weatherproof shelter for $1,394 in materials and approximately 60 man-hours of assembly labor. Compare this to conventional barracks: $12,000 in materials, 400 man-hours of skilled carpentry, 6 weeks construction time. Quansits deliver shelter at 1/10 the cost in 1/20th the time. By mid-1944, U.S. military deployed over 160,000 units to every combat theater. That's housing capacity for nearly 6 million personnel built in less than 2 years. Let me take you to specific battlefields where these steel shelters faced their ultimate tests. Guadalcanal, August 1942. First combat-deployed Quansit huts arrive on beaches where temperatures lumber at 95 degrees with 90% humidity. Japanese bombers make daily visits cratering anything looking like American infrastructure. Marine engineers unload flat-packed steel panels under sporadic artillery fire. Start bolting them together in coconut groves, still showing scorch marks from previous week's shelling. Within 12 hours, Henderson Field has 10 new structures housing maintenance crews for battered F-4F Wildcats operating from airstrips. Real tests come 3 days later when Japanese bombing runs score near misses. 500-pound bombs detonate 40 yards from huts full of aviation mechanics. Blast waves flatten surrounding palm trees. Shred canvas tents like tissue paper. But Quansits flex. Dirt and shrapnel rattle off corrugated steel. When smoke clears, structures stand intact with every man inside, shaken but alive. Jungle environments prove as hostile as enemy action. Within 2 weeks, red rust streaks appear on any ungalvanized fasteners. Salt air eats through standard hardware like acid. Fungus grows on everything holding moisture, turning inside surfaces into abstract art, exhibits of black and green mold. Ventilation louvers that seemed adequate in Rhode Island testing barely move, suffocating air. Marines start propping doors open 24/7. Cutting additional vent holes with tin snips, violating structural specifications but making huts livable. These field modifications get documented and sent back to Quansit Point, where engineers incorporate them into later production runs. More ventilation, larger louvers, every single fastener galvanized regardless of location. Iwo Jima, February 1945. The volcanic island offers different kinds of hell. Black sand blowing into every crevice, no topsoil for grounding stakes, constant threat of artillery from Mount Suribachi. Seabees arrive on D-Day +2, start assembling Quansit huts under fire, literally bolting panels together while mortar rounds impact 200 yards away. Volcanic sand proves impossible for traditional stake anchoring. Crews improvise by filling empty oil drums with sand. Cables connecting drums to huts' bases. When Pacific typhoons hit in March with 110-mile-per-hour winds, those improvised anchors hold while wooden structures across islands disintegrate. Base commanders' reports back to Pearl Harbor are succinct. Quansit huts survived, everything else gone. Arctic environments test designs from opposite extremes. Alaska's Aleutian Islands campaign sees Quansit huts deployed at Dutch Harbor and Adak, where temperatures plunge to -40. Winds regularly exceed 100 miles per hour. Cold makes steel brittle. Early units suffer from panels cracking at bolt holes. Engineers respond by specifying cold-rolled steel with different metallurgy for Arctic deployments, adding rubber gaskets at every joint to maintain flexibility. Heating huts creates its own problems. Warm air meeting frozen steel produces condensation, literally raining inside until crews learn installing insulation blankets, running ventilation even in sub-zero weather. By winter 1943, Weatherized Quansit models include internal insulation batting, double-wall construction for extreme cold zones, modified ventilation systems preventing heat loss while managing moisture. North Africa and Italy bring different challenges entirely. At Palermo, Sicily, Quansit huts pressed into service as ammunition depots take direct hits from German 80 mm artillery shells. Shells penetrate steel skins, detonate inside among crates of small arms ammunition. Resulting explosions should theoretically vaporize structures. Instead, arched shapes channel blast forces outward through walls and roofs in patterns leaving structural frames twisted but standing. EOD crews examining wreckage note that rectangular buildings would collapse completely, trapping anyone nearby under tons of rubble. Arch's inherent strength, that compression ring effect, means even catastrophic damage doesn't trigger total structural failure. Pacific typhoon season of 1944 delivers ultimate stress tests. Super Typhoon Cobra hits Philippines in December with winds measured at 140 miles per hour. 20-foot storm surge. At Tacloban, storms destroy 80% of all base structures. Wooden buildings explode into splinters. Concrete block structures collapse when wind undermines foundations. But of 43 Quansit huts on base, 39 survive intact. 4 suffer repairable damage. Bent panels and torn seams, but no total failures. Engineers analyzing survivors find that proper anchoring matters more than any other factors. Huts with adequate ground attachment ride out storms. Those with improvised or insufficient anchoring roll like tumbleweeds. By war's end, field performance data from 50 combat zones feeds back into continuous design improvement. 1945 production models bear little resemblance to 1942 prototypes. Better ventilation, stronger fasteners, improved insulation options, field-tested modifications turning good designs into exceptional ones. Now, jump forward to today's disasters and conflicts. You'll see the same engineering DNA resurging everywhere. When 2010 Haiti earthquakes destroy Port-au-Prince, relief organizations face identical equations American military planners confronted in 1942. Immediate shelter for hundreds of thousands of displaced people. No existing infrastructure. No time for conventional construction. Conditions destroying inadequate temporary housing within months. Solutions emerging borrow directly from Quansit principles, even when designers don't realize they're channeling 1940s military engineering. Arched steel frames, corrugated metal panels, prefabricated components shipping flat and assembling quickly. Basic formulas haven't changed because underlying physics and logistics haven't changed. United Nations High Commissioner for Refugees currently uses shelter systems called RHUs, refugee housing units, that are essentially Quansit huts with 80 years of material science improvements. Instead of corrugated steel, they use insulated composite panels. Instead of bolt-together assembly, they employ snap-fit connections. But core concepts remain identical. Curved profiles for structural efficiency and wind resistance. Self-supporting arches eliminating internal framing. Flat-pack shipping allowing massive quantities reaching remote locations. Assembly by unskilled labor with minimal tools. Two-person crews can erect modern RHUs in 4 hours, almost exactly matching 1942 Quansit specifications. These units currently house over 200,000 displaced persons in refugee camps across Africa, Middle East, and Asia. Hurricane-resistant construction has rediscovered arch geometry. After decades of building conventional rectangular structures, hurricanes repeatedly destroy. After Hurricane Katrina devastated Gulf Coast in 2005, engineers studying which buildings survived found curved structures consistently outperformed rectangular ones. Mississippi coast saw entire neighborhoods of conventional homes reduced to foundation slabs while handfuls of Quansit-style metal buildings stood intact with minor damage. This empirical evidence triggered research into what structural engineers call aerodynamic architecture, designing buildings working with wind forces rather than resisting them through brute strength. Results look remarkably like Quansit's because physics haven't changed. Wind flowing over curves creates less pressure than wind slamming into flat surfaces. Today, exactly as it did in 1942, modern tiny house movements unknowingly reinvent Quansit principles when designers seek maximum interior space with minimum materials and cost. Several companies now manufacture arch-roofed prefab cabins using same corrugated metal and self-supporting curves Otto Brandenburger pioneered. These sell to buyers seeking affordable housing, disaster-resilient structures, off-grid living solutions. Marketing emphasizes sustainability and modern design. Rarely mentioning fundamental architecture is World War II military shelter. Some high-end architectural firms rehabilitate aesthetics, designing luxury versions with floor-to-ceiling glass end walls and premium finishes costing $300 per square foot while maintaining signature curved profiles. Arches have gone from utilitarian necessity to design statements. Military applications never actually stopped. U.S. armed forces still deploy arch-style shelters in conflict zones. Afghanistan, Iraq. Classified locations all feature modern descendants of original Quansits. Current military specifications call for units helicopter-lifted to mountain bases. Assembled in combat conditions, surviving IED blast waves, materials have evolved. Aluminum alloy frames, Kevlar reinforced panels, climate control systems. But if you showed 2025 military deployable shelters to 1942 Quansit point engineering teams, they'd immediately recognize their own design philosophy. Recent innovations are expandable versions deploying from shipping containers, unfolding like origami, locking into rigid arch structures within hours. Economic arguments justifying Quansit huts in 1942 remain compelling today. When disasters strike or rapid deployment is required, conventional construction simply cannot compete on speed or cost. Modern engineered arch shelters deliver weather protection for approximately $50 per square foot, including shipping and assembly. Conventional construction in same locations, assuming contractors are even available, costs $150 to $300 per square foot, requires months instead of days. For humanitarian organizations operating on donor funding or military logistics managing trillion-dollar budgets, these cost differentials matter enormously. Math driving Quansit development. How do you shelter the most people for least money in shortest time? Hasn't changed, because scarcity economics haven't changed. Perhaps ultimate validation comes from space exploration. NASA and private space companies designing Mars habitats keep arriving at Quansit-like solutions. Proposed Martian shelters feature arched profiles resisting planets' severe dust storms, prefabricated components shipping on spacecraft, self-supporting structures not requiring extensive foundation work in Martian regolith. Constraints of interplanetary construction mirror Pacific theater challenges of 1942 so precisely that engineers independently rediscover same solutions. Extreme environments, minimal tools, unskilled assembly, maximum strength from minimum materials. When humans finally build permanent shelters on another planet, there's reasonable chance those structures will owe design heritage to 30 engineers working in Rhode Island warehouses during World War II's darkest days. solving impossible problems with corrugated steel and brilliant simplicity. The curved steel buildings that once housed bomber crews through Pacific typhoons may someday shelter astronauts through Martian dust storms. Same physics, same solutions, same human ingenuity, making the impossible inevitable.